welcome to AC Lesson 4, Part 4, our final part. Dr. Ken here with you again. Now, Part 4, we're looking at series resonance. Basically, when the capacitive reactance of the circuit equals the inductive reactance of the circuit, it's said to be in resonance, or it is purely resistive. No, that sounds a bit crazy, but that's the way it is. Now, if you can remember from last time, or the last couple of lessons, if we looked at inductive reactance, and we've got a graph here, and you'll notice on the graph, the horizontal of the graph is frequency, so our frequency is coming from 0 up to 150 Hertz here, and our reactance in ohms is on the vertical scale. If we were to plot the inductive reactance, we would get this blue line. As the frequency goes up, if you remember, the reactance also goes up. So for inductive reactance, as frequency increases, the reactance goes up. But if you remember, for capacitors, they're exactly the opposite. As the frequency goes up, their capacitive reactance goes down, and you can see me tracing the orange curve here. So at some point, the two curves are going to cross here in the center, just where my cursor is. So you can actually plot that down on the curve, and that's what we call the point at which the circuit is resonant. In other words, XC and XL both equal the same amount, but they're 190 degrees out from each other, so they cancel each other out. To just explain that a little bit further, if we come over to the table here on the right hand side, you can see we've got frequency in the first column on the left hand side, XL inductive reactance calculated, and then XC capacitive reactance calculated for this circuit here. So as the frequency goes up and up and up, you can see the inductive reactance is getting smaller and the capacitive is the inductive is getting larger and the capacitive is getting smaller, but at around about 100 Hertz, you can see one's at 157, one's at 159. Basically, they're cancelling each other out. And the only thing left in the circuit to restrict current is this resistor. So that's why we say a resonant series circuit, when it's in resonance, it's purely resistive, because only the resistive component is left in the circuit that is restricting the current. So in an RLC circuit with a resonant frequency close to 100 Hertz, resonance is going to be when XL and XC equal each other. In this particular case, it's very close to 100 Hertz. So we have an equation, and you can find this equation on your equation sheet. I'd suggest you take a few seconds now and go and make sure you can find this equation on your equation sheet. Sometimes they have FR for little subscript R. Sometimes they'll have a little subscript O for oscillate. So sometimes it's F subscript R, sometimes F subscript O. But frequency at resonance is equal to 1 on 2 pi square root of LC. So FR is a resonant frequency in Hertz. 2 pi, a good old 2 pi, it crops up everywhere at 6.28. And our inductance is in henries, and our capacitance is in farads. So our formula for finding the resonant frequency is pretty simple, pretty easy to remember. 1 on 2 pi square root of L times C. So here's a little example. This is example 17.9 from the textbook. And we've got 10 ohms, so voltage across the resistor is in green. Voltage across the inductor at 0.25 henries or 250 millihenries. And the voltage across the capacitor VC. So 200 volts is the supply. So our frequency at resonance is going to be 1 on 2 pi square root LC. So 1 on 6.28 square root of 0.25 times 10 times 10 to the minus 6. Now 0.25 is simply henries. Our 10 is our 10 microfarads, but remember it's in micros, so we have to do 10 multiplied by 10 to the minus 6. And the actual exact frequency is 100.71 hertz. So very close to 100 hertz is the resonant frequency. So here's a table. Now this is a very, very important table, and I'm going to explain to you why. The columns that are very, very important to us are the volts across the inductor and the volts across the capacitor. So here's the frequency down the left hand side. Here's the frequency 50 through to 150. In bold, you can see we're going to resonate at 100 hertz, and you can see our Z of our circuit starts at 240, drops down to 10. Remember, the only thing left in the circuit was that 10 ohm resistor, and then it goes back up again as the frequency increases past the resonant point. You'll notice our current starts quite low because our reactances are restricting the current. We get to our resonant point where only the resistor is restricting the current, so we end up with about 20 amps flowing in the circuit. Then the current drops off again as the frequency increases up to 120, 150. Voltage across the capacitor, voltage across the resistor is the first one. Voltage across the resistor VR starts low, gets up to about 200 volts. Still quite a large voltage across the resistor. Okay, of course, that is the applied voltage. If you remember, it had 200 volts to start with, and 35 volts, then down to 15 as the frequency goes up to 150. But here's the one that I really, really want you to take note of. And I'm just going to change my pointer a little bit because I want to draw around it. You can see here 65 volts, 330 volts, it's climbing. Look at this. As it gets near 3,000 volts, and then at resonance, look at that voltage. 3.1 kV. It's huge. So at resonance, you're going to get very high voltage across the reactive components. And you'll see it also on XC. You're going to get very high voltages across the reactances. Again, they're both exactly the same voltages because they're both the same reactance values, but at 90 degrees out from each other. Very high voltages. What's going to happen here is any capacitors there are in the circuit, they're probably only built to handle about 400 or 500 volts. So the capacitor is going to break down. Also, the inductors in the circuit, might get insulation breakdown because of these very, very high voltages. The other thing to note, of course, is that the phase angle comes to unity. So at resonance, the phase angle comes to 0 degrees because the only thing left in the circuit is the 10 ohms that's restricting the current. So only resistance is left in the circuit, therefore we are at 10 ohms. So it's very important to remember. So at resonance, the current got up to 20 amps, the maximum current that could flow through a 10 ohm resistor. That's the only thing that was restricting the current. And the voltages across the capacitor and the inductor are both this whopping 3.2 kV. So capacitors will break down, inductors will break down. You'll have all kinds of insulation problems. Now let's look at the response curve. And again, here's our little circuit diagram. We've got 10 ohms, 250 millihenries and 10 microfarads in our circuit. And if we look at our curve, we've got frequency on the horizontal, and we've got the current this time on the vertical. So as we come closer and closer and closer to resonance, where the current hits the maximum, you can see a very sharp curve, very sharp needle-like shape on the thing. So the frequency response is very sharp. So at resonance, in a series RL circuit, current is at its maximum and circuit impedance, which is only left in this particular case by the resistor, is the only thing that restricts the current. If that resistor was not there, then the only thing that would be restricting current is the resistance of the wire that is connecting the components together, and you would get extraordinarily high currents. So in this particular case, we only get up to 20 amps because we have 10 ohms in the circuit, and the capacitor and the inductor cancel each other out completely at this point we call resonance, which in this particular case happens at 100 hertz. So there's a thing called Q factor. The resistance of a series RL circuit determines how the circuit behaves at resonance. The amplifying effect is caused at resonance is called a Q factor or a quality factor. But because these circuits are actually used in radio communications as filters, they are called Q factor or quality factor. The tinier and sharper the point is, the better the Q, or the more resonant or the more filtering you can create with that particular circuit. The higher the resistance of the circuit, the lower the Q factor. So if you've got higher resistance, then the Q will be lower. So voltage to ratio, to find the Q factor. Q factor equals the ratio of the voltage across either reactive components and the voltage drop across the resistance. So Q is equal to the voltage across the L divided by the voltage across the supply. So voltage across the C divided by the voltage across the supply, where voltage is across the resonance, VL and VC equal each other, so we just call it, so in this case VL, VC will be the same because they equal each other, and the voltage across the resistor at resonance is of course the supply voltage. We saw that in our little table previously. So the X and R ratio to find the Q factor. In a series RLC circuit, Q equals the ratio of the resistance of the capacitor and the inductor at resonance. So Q can equal XL divided by R or XC divided by R. Again, reactance where those values are occurring at resonance only when XL and XC equal each other. So resonance only happens when those two equal each other, and we can find the Q simply by taking the XL and dividing it by the R in the circuit. So bandwidth, you can see here in A, you can see we have a high Q, which means there must be a high amount of resistance. So the bandwidth in here, or how much the circuit will or will not let through, is very narrow. And the way that is determined is between 70% and 100%. So it's 70.7. Do you remember that number? That's RMS. So at our RMS point is where they measure the bandwidth. There's what they call the lower frequency and the upper frequency. So the bandwidth is in that range of frequencies where the circuit current is greater than 71% of the maximum value. In diagram B, the Q is low, very wide bandwidth, and a very blunt top of the curve. High Q, very sharp curve. Low Q, very blunt curve and very much wider bandwidth, high Q, narrow bandwidth. So in radio circuits, that's what they're looking for. They're always looking for this one here. Try and get the Q as narrow as possible. So when you tune to a particular radio station or frequency, that's what you're letting through. You're letting through only the frequencies that sit inside the Q. And we can also use this in electrical substation systems, which we'll look at in a moment. So the equation to find the bandwidth. Bandwidth depends on the Q of the circuit, which in turn depends on the resistance of the circuit. So the equation is bandwidth is simply the frequency resonant, the resonant frequency, divided by the Q of the circuit. So the bandwidth is a frequency bandwidth in hertz. FR is the resonant frequency, and Q is the Q factor or the quality factor. So the closer you can get that, or the higher you can get the Q, the narrower the bandwidth will be. Applications for series resonance, and here you can see coils. There's 3 of them, one for each of the 3 phases. There's a capacitor, and here are the incoming tones. And what they're doing here is they're injecting particular frequencies onto the mains. So they've got the tones coming in through this cabling here. It's being injected through this combination of these capacitors. You can see the capacitors, there's 2 of them sitting in the back of the circuit there. These inductors, and then up to the 11 kV. So the 11 kV has these tones superimposed, and the reason for the tones is to turn your hot water services on and off. So each of the supply authorities has a particular set of tones, and they can turn everyone's hot water services on and off, or they can turn only a part, depending on what frequency your particular hot water service relay has been set up for. So this is a series resonance circuit. It is used in substations to couple control tones to high voltage distribution cables for the purpose of turning on and off off-peak hot water services. So in summary, when a series RLC circuit is at resonance, 1. The reactive components cancel each other out. Only the opposition to current flow is the resistance left in the circuit. Impedance of the circuit only equals the resistance in that circuit, because the capacitive reactance and the inductive reactance is key to cancel each other out. So you're only left with the resistance in the circuit. The impedances of the circuit is at its minimum at resonance, so the current is at its maximum. And finally, the current is in phase with the applied voltage, which means the circuit is at unity or a power factor of 1 or a phase angle of 0 degrees. Summary 2, when a series RL circuit is at resonance, voltages across the inductors and the capacitors equal to and are often much, much higher than the applied voltage. Because the voltages across the capacitors and the inductors are often very high, if resonance does occur, then capacitors break down and inductors, their insulation breaks down. And finally, the voltage across the capacitor is 180 degrees out of phase with the voltage across the inductor, and when they both equal the same, that is why they cancel each other out completely. I've also added some YouTube clips to this particular lesson, which you'll see as separate links. So I've got you one on RLC in series, runs for about 13 minutes. I've got you one on resistance, reactance and impedance, goes for 8 minutes, quite interesting one. And series resonance, it's only 5 minutes long, it's worth a watch. Really introduce you to series resonance, and some of the things that it's applied to the way we use series resonance. Series resonance can be a helpful thing, great for putting control tones on the mains. It can be a terrible thing if you get a resonance circuit out in the field, maybe with a long power line and a transformer that's feeding it, for example. So that's the end of lesson 4.4.